Welcome to today's session. In this video, we'll explore problem number 1062, titled Longest Repeating Substring. This problem challenges us to identify the longest substring that repeats within a given string. We'll discuss different approaches to solving it, their trade-offs, and complexities. Let's dive in and tackle this coding problem together. In this problem, we are tasked with finding the length of the longest substring within a string S that appears at least twice. These occurrences are allowed to overlap. If no repeating substring exists, the result should simply be 0. For the input format, we are provided with a single string S. The output is an integer, which represents the length of the longest repeating substring. For example, if the input string is S equals ABCD, the output would be 0 because there are no substrings that repeat within the given string. To explain further, in the case of the input S equals ABCD, no substring occurs more than once, so the result is 0. Now take a different input, S equals ABABA. Here, the substring AB appears twice in the string, and there is no longer substring that repeats. Therefore, the output is 2. Another example is the input S equals ABCABDAB where, as we will see, the result is determined by analyzing the repeated substrings. For the input S equals ABCABDAB, the output is 3. This is because the substring AB appears 3 times in the string, once starting at index 0, again at index 4, and finally at index 8. There are no substrings longer than AB that repeat within the string. Looking at the constraints, the length of the string is capped at 10⁻⁴, meaning our solution must be efficient enough to process very large inputs. Additionally, since the string consists solely of lowercase English letters, we are working with a limited character set, which simplifies pattern detection. Keep these constraints in mind when designing an algorithm. Considering edge cases, if all the characters in the string are unique, such as S equals ABCDEF, the output will always be 0 because there are no repeating substrings. On the other hand, if the string consists entirely of identical characters, like S equals AAA, the longest repeating substring will be the entire string minus 1 character, which in this case would be 3. Finally, if the string contains overlapping repeating substrings, such as S equals ABABAB, overlaps need to be accounted for, and the result will depend on the longest repeating substring. These scenarios highlight the importance of carefully analyzing the structure of the input string to derive the correct result. Let's start by discussing the brute force approach. The intuition behind this method is straightforward. We systematically examine all possible substrings of the input string, S, to check if any of them appear more than once. To do this, we vary the substring lengths, starting from the longest possible and decreasing the length until we find a repeating substring. The steps involve generating all substrings, checking each one for multiple occurrences, and returning the length of the longest repeating substring we find. However, this approach has significant drawbacks. The time complexity is O(n) cubed, because generating all substrings takes O(n) squared, and checking if a substring repeats takes O(n). Additionally, this approach does not use any extra data structures, so its space complexity is O(1). While simple, this method becomes computationally expensive and impractical for large strings, making it unsuitable for efficient problem solving. To address this, we turn to an optimized approach that combines binary search and hashing. Now, let's explore the optimized approach using binary search and hashing. There are a few key observations that form the foundation of this strategy. First, if a substring of length k is repeating, then all substrings of length k1 must also be repeating. This allows us to use binary search on the length of the substring, significantly reducing the number of substring checks. Additionally, hashing enables efficient comparison of substrings, making it faster to identify duplicates. The steps involve using binary search to find the maximum length of a repeating substring, with the search space ranging from 0 to n1. For a given length, mid, we use a rolling hash or a set to check if any substring of that length repeats. This involves computing hashes for all substrings of length mid and storing them in a set. If a duplicate hash is found, it indicates a repeating substring. Based on the result, we adjust the binary search bounds and continue until the maximum length is identified. This approach runs in O(n) log n time, as binary search takes O log n, and hashing all substrings of a given length takes O(n). The space complexity is O(n) for storing the hashes. This method is faster than brute force and scales well for larger strings, making it an excellent choice for this problem. Additionally, there's the suffix array approach, which provides another efficient way to solve the problem. A suffix array stores all suffixes of a string in sorted lexicographical order. By computing the longest common prefix, or LCP, of adjacent suffixes in the sorted array, we can determine the longest repeating substring. The steps are clear. First, construct the suffix array, which can be done in O, n log n. Next, compute the LCP array, which stores the length of the longest common prefix for each pair of adjacent suffixes. The maximum value in the LCP array corresponds to the length of the longest repeating substring. This method is advantageous because it is efficient for large strings and provides additional insights into the structure of the input. The time complexity is O, n log n, for constructing the suffix array, plus O, n, for computing the LCP array, while the space complexity is O, n, for storing these arrays. Although it is an effective method, its implementation can be complex, requiring a deeper understanding of string algorithms. For this problem, we've chosen the binary search and hashing approach due to its balance of simplicity and efficiency. While the suffix array method is theoretically efficient, constructing the array and computing the LCP can be more complex to implement, especially for those less familiar with advanced string algorithms. In contrast, the binary search and hashing technique is more straightforward and leverages widely used algorithms like Rabencarp. This approach avoids the computational cost of brute force while maintaining a manageable level of implementation complexity. There are trade-offs to consider. The suffix array method may outperform the chosen approach for extremely large strings, but its complexity can be a barrier. On the other hand, hashing is susceptible to collisions, but with a well-designed hash function, this risk is minimized. The final complexity of the chosen approach is O, n log n, in time and O, n, in space, making it both fast and space-efficient for solving the problem effectively. To solve the problem of finding the longest repeating substring in a given string, we first need to understand the goal. A repeating substring is one that appears at least twice, and these appearances can overlap. A brute force approach to this problem would involve generating all possible substrings of the input string and checking if any of them occur more than once. To make this efficient, we start by considering the longest possible substrings and work our way down to shorter ones. The first step is to initialize some variables. We'll use n to represent the length of the string s, max_length to track the length of the longest repeating substring we've found so far, and result to store that substring itself. With these preparations, we can systematically search for the solution. Next, we need a systematic way to generate and check substrings. We begin with an outer loop that starts at the longest substring length, which is n1, and decreases down to 1. For each substring length k, we generate all possible substrings of length k. This is done using a sliding window approach, where we slide a window of size k across the string to extract substrings. For each starting index I from 0 to nk, we extract the substring s, I plus k. To check if a substring repeats, we use a hash set called scene. If the substring is already in the set, it means we've encountered it before, so it's a repeating substring. In that case, we check if it's longer than the current max_length. If it is, we update both max_length and result to reflect this new substring. If the substring is not in the set, we simply add it to scene and continue. Additionally, if we find a repeating substring of the current length k, we can terminate early since longer substrings are checked first, ensuring efficiency. Finally, once all iterations are complete, we return the result. If no repeating substring is found during the process, we return an empty string as the output. There are some key insights that make this approach effective. Starting with the longest substrings allows us to potentially terminate early as soon as a repeating substring is found, which reduces unnecessary computations. The sliding window technique ensures that all substrings of a given length are generated efficiently without the need for deeply nested loops. Using a hash set for repetition checks is crucial because it allows constant time lookups, making the approach significantly faster. The ability to skip shorter substring lengths entirely after finding a repeating substring further optimizes the overall algorithm. These combined strategies make the brute force approach as efficient as possible within its design. To implement this algorithm, we rely on two main data structures, strings and hash sets. Strings are used to represent the input S and the substrings extracted during the process. The hash set serves as a collection to store substrings and efficiently check for repetitions. Now, let's evaluate the complexity of this approach. The time complexity is dominated by the process of generating all substrings, which, in the worst case, involves n³ operations. This is because for each substring length, we generate up to n substrings, and substring extraction itself can take n time. Checking for repetition in the hash set is an O(1) operation, so it doesn't significantly add to the overall time complexity. For space complexity, the hash set can store up to n² substrings in the worst case, as there are roughly that many possible substrings in a string of length n. While this approach is not the most optimal in terms of complexity, it's a straightforward way to solve the problem. Let's now go through an example to see how the brute force algorithm works in practice. Consider the input string s equals banana. We start with the outer loop where k equals 5, meaning we're looking at substrings of length 5. The substrings generated are banan and anana, but neither of these repeats. Next, we move to k equals 4, where the substrings are bana, anan, nana. Here, we find that nana repeats. Since this is the first repeating substring we've encountered, we update max_length to 4 and result to nana. Because we've found a repeating substring, we terminate early without checking shorter lengths. The output for this example is therefore nana. This walkthrough highlights how the algorithm efficiently narrows down the search space by prioritizing longer substrings first and terminating as soon as a solution is found. This is a complete Python solution for LeetCode problem number 1062, longest repeating substring. The problem involves finding the longest substring within a string S that appears at least twice. To solve this efficiently, we use a binary search approach combined with a helper function to check for repeating substrings of a given length. The longest repeating substring function starts by defining a nested helper function, has_repeating_substring. This helper checks if there is any substring of a given length that repeats within S. To do this, it iterates through all substrings of the given length, storing each one in a set. If a substring is already in the set, it means it repeats, and the function returns true. Otherwise, it keeps adding new substrings to the set. If no repeats are found, the function returns false. Next, we use binary search to find the maximum length of a repeating substring. The binary search operates on the range of possible substring lengths, starting from 1 up to the length of S. The midpoint of the range is tested using the helper function. If a repeating substring of that length exists, we move the search range to the right, longer lengths, and update the result. Otherwise, we move the range to the left, shorter lengths. The binary search continues until the range is exhausted. At the end, the variable result holds the length of the longest repeating substring. This approach is efficient because it avoids generating all possible substrings explicitly and instead narrows down the possibilities using binary search, making the solution suitable for longer input strings. The time complexity of this solution is approximately n² log n, where n is the length of the string. This comes from the binary search, log n, and the nested substring checks, n² in the worst case. The space complexity is n, due to the use of the set for storing substrings. Here, we begin implementing the solution in Java for finding the longest repeating substring. We start by defining the longest repeating substring method, which takes a string S as input. Inside this method, we define a helper function called hasRepeatingSubstring. This helper checks if there exists a repeating substring of a given length in the input string. To do this, we use a hash set to keep track of all the substrings of the specified length that we've encountered so far. For each substring within the valid range, we check if it already exists in the set. If it does, we know there's a repeat, so we return true. Otherwise, we add the substring to the set and continue. If no repeats are found after checking all substrings of the given length, we return false. Next, we initialize 2 pointers, left and right, to represent the bounds of our binary search. Left starts at 1 because the shortest valid substring length is 1, and right is set to the length of the input string. We also initialize a variable result to store the maximum length of a repeating substring found so far. Then, we use a binary search loop to systematically check for the longest repeating substring length. The midpoint of the current range, mid, is calculated using left plus right left /2. If the helper function confirms that a repeating substring of length mid exists, we update result to mid and shift the search to the right half by setting left to mid +1. On the other hand, if the helper function determines that no repeating substring exists for the current length, we adjust our search range by moving the right pointer to mid 1. This ensures that we narrow the search to smaller substring lengths. The binary search continues until the left pointer exceeds right, at which point we exit the loop. Finally, after the binary search has completed, we return the value stored in result, which represents the length of the longest repeating substring found in the input string. This approach efficiently combines the use of a helper method for substring checks with a binary search mechanism, ensuring that we achieve an optimal time complexity for solving the problem. To solve the problem of finding the longest repeating substring, we start with a simple example where the input string is s equals abcd. The first step involves setting up a binary search range. Here, left is initialized to 1, and right is set to the length of the string, which is 4. We also initialize a variable result to 0, which will eventually store the length of the longest repeating substring. Next, we proceed with the first iteration of binary search. We calculate the midpoint, mid, as the average of left and right, which gives us 2. We then check if there is a repeating substring of length 2 using a helper function called has_repeating_substring. To do this, we iterate over all substrings of length 2, namely, UB, BC, and CD. As we process these substrings, we add each one to a set called scene. Since no duplicates are found in the set, the helper function returns false, indicating that no repeating substring of length 2 exists. As a result, we update the binary search range by setting right to mid 1, which reduces it to 1. In the next step of the binary search, we calculate the new midpoint, mid, as left plus right, //2, which now evaluates to 1. This time, we check for repeating substrings of length 1. Again, we initialize an empty set called scene and iterate through all substrings of length 1, which are A, B, C, and D. As before, we add each substring to the set, and no duplicates are encountered. The helper function returns false, confirming that no repeating substring of length 1 exists. At this point, we update the binary search range again by setting right to mid 1, which now makes right equal to 0. Since right is less than left, the binary search terminates. The value of result, which remains 0, is returned as the final output, indicating that the input string abcd does not contain any repeating substrings. Now, let's consider another example with the input string s equals abcab. For this input, we begin by setting the binary search range with left equal to 1 and right equal to the length of the string, which is 7. We also initialize result to 0. For the first iteration of binary search, we calculate mid as left plus right, //2, which gives us 4. We then check for repeating substrings of length 4. Using the helper function, we initialize an empty set scene and process substrings of length 4, namely AABC, ABCA, CA, and COB. As we add these substrings to the set, no duplicates are found. The helper function returns false, indicating that no repeating substring of length 4 exists. Consequently, we update right to mid 1, reducing it to 3. In the second iteration of binary search for the string s equals abcab, we calculate mid as left plus right, //2, which results in 2. We now check for repeating substrings of length 2. As usual, we initialize an empty set scene and process substrings of length 2, AA, UB, BC, CA, and another AA. This time, the substring AA appears twice, which is detected as a duplicate. The helper function returns true, confirming the existence of a repeating substring of length 2. We update result to mid, making result equals 2, and adjust the binary search range by setting left to mid +1, which increases it to 3. In the third iteration, mid is recalculated as left plus right, //2, which gives us 3. We now check for repeating substrings of length 3. Substrings of length 3 include OB, ABC, CA, CAA, and another OB. The substring OB appears twice, so the helper function again returns true. We update result to mid, setting it to 3, and further adjust left to mid +1, making it 4. With left now greater than right, the binary search ends. The final value of result, which is 3, is returned as the length of the longest repeating substring. Let's explore one final example where the input string is s equals AAAA. We start the binary search with left set to 1 and right set to the length of the string, which is 5. We initialize result to 0. In the first iteration, we calculate mid as left plus right, // 2, which evaluates to 3. We then check for repeating substrings of length 3. Using the helper function, we process substrings of length 3, AAA and another AAA. The substring AAA appears twice, so the helper function returns true. We update result to mid, setting it to 3, and increase left to mid plus 1, making it 4. In the next step of the binary search for the string s equals AAAA, we calculate mid as left plus right, // 2, which results in 4. We now check for repeating substrings of length 4. Substrings include AAAA and another AAAA. The helper function detects a duplicate, returning true. We update result to mid, setting it to 4, and adjust left to mid plus 1, increasing it to 5. In the final iteration, mid is recalculated as left plus right, // 2, which gives 5. This time, we check for repeating substrings of length 5. The only substring is AAAA, and no duplicates are found, so the helper function returns false. We update right to mid 1, reducing it to 4. With right now less than left, the binary search terminates. The final value of result, which is 4, is returned as the longest repeating substring length. To analyze the time complexity of this algorithm, we start with the binary search component. The binary search operates over the possible lengths of substrings, ranging from 1 to the length of the string s. This gives a maximum of O log n iterations, where n is the length of the string. Next, for each potential substring length, the has_repeating_ substring function is used to check if a repeating substring of that length exists. This function iterates over all possible substrings of the given size. If the substring length is length, there are approximately n length plus 1 substrings, which simplifies to O n in the worst case. For each substring, operations such as comparison or insertion into a set are performed, which take O length time. As a result, the time complexity for the has_repeating_ substring function is O n asterisk length. Now, combining the two components, the binary search calls has_repeating_ substring multiple times for different substring lengths. In the worst case, the substring length can range from 1 to n, multiplying the number of binary search iterations, which is O log n, by the cost of a single has_repeating_ substring call, which is O n asterisk length. We get a combined complexity of O log n asterisk O n asterisk length. Substituting the maximum value of length as n in the worst case, this simplifies further to O log n asterisk O n squared, which equals O n squared asterisk log n. Therefore, the overall time complexity of the algorithm is O n squared asterisk log n. Shifting focus to the space complexity, we start by analyzing the auxiliary space used by the has_repeating_ substring function. This function employs a set called scene to store substrings of size length. In the worst case, the set contains all unique substrings of the given size. The number of substrings is at most O n, and each substring of size length requires O length space. If the substring length is equal to n in the worst case, the space required for the set becomes O n asterisk length, which simplifies to O n squared. Additionally, the binary search itself only uses a constant amount of space for variables like left, right, and mid, which is O 1. When combining these components, the space complexity is dominated by the scene set, leading to an overall space complexity of O n squared in the worst case. Let's compare this optimized approach to a brute force solution. A naive method would involve generating all possible substrings of the string s and then checking for duplicates. Generating all substrings takes O n squared time since there are about that many substrings. Comparing these substrings for duplicates could take up to O n time per comparison. This results in a total time complexity of O n cubed for the brute force method. In contrast, the optimized approach leverages binary search and a sliding window to minimize the number of substring comparisons. This reduces the time complexity to O(n squared asterisk log n), which is a significant improvement, especially for larger input strings. The key advantage here lies in the reduction of redundant operations while still systematically exploring potential solutions. Now, let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, if the input string has no repeating substrings, the binary search performs fewer iterations, and the has_repeating_substring function returns early. However, the asymptotic complexity remains O(n squared asterisk log n). In the average case, the binary search typically performs O log n iterations, and the has_repeating_substring function processes O(n) substrings of varying lengths. Again, the overall complexity remains O(n squared asterisk log n). In the worst case, such as when the string consists entirely of repeated characters like AAAAA, the algorithm must check all possible substrings, resulting in a time complexity of O(n squared asterisk log n). Mathematically, this happens because the binary search involves O log n iterations, and each iteration of has_repeating_substring processes O(n) substrings of length up to n. The total runtime is therefore O log n asterisk O n asterisk O n, which simplifies to O(n squared asterisk log n). As for space complexity, it is dominated by the scene set, which can store up to O(n) substrings of size O(n), leading to O(n squared) space complexity. When solving the longest repeating substring problem, there are several common mistakes to watch out for. First, overlooking edge cases can lead to significant issues. For example, forgetting to test scenarios like an empty string, a single character string, or a string with all repeated characters, like AAAA, can cause incorrect results or even runtime errors. This happens because some algorithms assume strings have varying characters or a minimum length, which isn't always the case. Another common mistake is implementing a brute force solution without optimization. Naive approaches that check all possible substrings can lead to a time complexity of O(n cubed, or worse, which is impractical for large inputs where n can go up to 10,000 or more. Lastly, errors in sliding window or hashing logic are frequent. For instance, failing to shrink the sliding window properly or mishandling hash table collisions can lead to incorrect or missed duplicate substring checks. These mistakes can all result in failure to meet performance or correctness requirements. Another pitfall involves misunderstanding the problem requirements. A common confusion is mixing up substring and subsequence, or misinterpreting constraints like case sensitivity or allowed character sets. Misreading the problem can lead to an entirely incorrect approach. Additionally, ignoring space complexity can cause problems. For instance, storing all substrings in a list or hash table can consume excessive memory, especially when a rolling hash would suffice. This can lead to memory overflow for large inputs. To perform well in interviews, it's important to recognize key patterns. Substring problems often benefit from techniques like sliding windows or hashing. For example, Rabin-Karp and rolling hashes allow efficient substring comparisons without storing them explicitly. Interviewers also expect optimization. While a brute force solution might work for small cases, achieving O(n log n) complexity with binary search and hashing is often a benchmark to aim for in problems involving duplicate substrings. Beyond optimizing your solution, clear communication is vital in interview settings. It's essential to articulate the trade-offs between different approaches, such as comparing brute force with optimized hashing. This demonstrates a deeper understanding of the problem and its constraints. Practical debugging is another critical skill. Walking through small input examples helps verify that your approach is robust, and highlighting edge cases shows your attention to detail. There are also related problems that can help deepen your understanding of this topic. For instance, LeetCode 1044, longest duplicate substring, is closely related and requires similar techniques. Other problems, like longest substring without repeating characters, LeetCode 3, and repeated DNA sequences, LeetCode 187, also explore substring detection but with slightly different constraints. Lastly, longest palindromic substring, LeetCode 5, introduces techniques like dynamic programming, which can complement your knowledge of efficient string algorithms. Finally, there are alternative approaches to solving substring problems, each with its own trade-offs. Sliding window techniques are straightforward to implement and often involve using a hash set to track substrings. While simple, these approaches are highly effective and typically have a time complexity of O(n), assuming a good hash function. Binary search combined with hashing is another powerful technique. Although more complex to implement, it achieves a better time complexity of O(n log n). This approach is particularly useful for large input constraints but requires careful handling of rolling hash implementations. Lastly, advanced data structures like suffix arrays or suffix trees offer optimal solutions for substring problems. These methods can achieve complexities of O(n) to O(n log n), depending on the implementation. However, they are considerably harder to implement, so they're best explored once you've mastered the basics of string algorithms. Understanding these trade-offs allows you to tailor your approach based on the problem's constraints and requirements. Great job following along. In summary, we tackled the longest repeating substring problem, explored different approaches, and highlighted key insights. Always remember to weigh the trade-offs between brute force and optimized solutions. Thank you for watching, and don't forget to like, comment, and subscribe for more exciting coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!